All right, so in this lesson, we're going to open up the discussion on extreme values of functions. And you did some of this in pre-calculus, probably with sort of an observational look at it, which means you probably looked at a graph and maybe used some tools on your calculator to determine extreme values, maxes, mins, etc. You probably learned kind of a surface definition of an absolute max or a global max versus a local one. And that definition will kind of be addressed a little bit here in this video. But the first thing we need to talk about is something that seems really intuitive and obvious, and that is the extreme value theorem. If f is a function that is continuous on a closed interval from a to b, then f is guaranteed to have both a maximum and a minimum value on that interval. Okay, now when we talk about max values and min values, we need to keep in mind that we're referring to y values. So you're talking about how big the function gets on y and how little the function gets on y, up and down in that order. Now, this makes just a ton of sense. I mean, if we've got just a graph of a function, let's just call it f of x, and it is continuous from a all the way to b, then you know it's got a maximum and a minimum value. I mean, it's pretty seriously easy to point out that being the minimum value and that one being the maximum value. Super easy to do and super easy to understand. But the big question is, how do we get there? And especially when graphs don't always take on this particular shape. Every different function has a graph that obeys different properties and characteristics. So how do we take kind of a one-size-fits-all approach to finding those extreme values? Well, let's take a look at some examples here and see what they mean by that. You will notice that in this particular picture, this is a graph of a function, and we've got some absolute maxes, absolute min, local max, local min. I want to point out something rather fascinating. If you notice at this local max and this local min, the derivative of the function would be 0 because it looks like we have a horizontal tangent in both places. You might also note here that we're not differentiable. You see that sort of hybrid between a cusp and a sharp corner, or maybe it's just something that proves it's not differentiable, like a strange function does from time to time. And then we have to consider our endpoints as well. Because it's a closed interval, our maxes and mins could occur at endpoints. That's a definite possibility. Okay, so now this opens the door to the question, what do we do to find those values? The biggest thing that we can point out, once again, is that right here, f prime of x is probably equal to 0. And f prime of x is probably equal to 0 at that point c. And here we could make the claim that f prime of x does not exist, not differentiable at that point. Okay, well, that narrows the field a bit and allows us to make a bit of a definition here. And that definition is this one. It's the definition of a critical point. A point that is on the interior, okay, so emphasis on interior, somewhere in between a and b. A point that is in the interior of a domain at which either f prime of x is 0 or f prime of x does not exist. Okay? Those are two spots where we will find critical values of our function f. Now, I want to point out something a little bit interesting here, just a quick little bit of vocab. If f prime is 0 on an interior point, it's what is said to be a stationary point. You might run into that on some verbiage from time to time in certain problems, but I don't think it's really super important, but it might come up, so that's good information to know. Let's practice on how you find a critical value. Let's just do that really quick, starting with this example right here. And I could rewrite this example with a negative exponent because that's just going to be so much easier to do when it comes to taking the derivative. In order to find critical values, I need to find the derivative and then analyze that. So as I go to find f prime of x, I'm going to do my power chain rule here. So negative 1/2 times 4 minus x squared to the negative 3/2 when I drop that power by 1. And then I can't forget the chain rule, so I'm going to multiply by negative 2x. And a little bit of cleanup later, cleanup on aisle 2 as I like to joke. The x's wash out, the negatives wash out, and you're going to end up getting something like this. X over the quantity of 4 minus x squared raised to the 3/2. Now, lucky for us, finding out where this is 0 and undefined isn't going to take a whole lot of effort. This is just kind of like finding, all that stuff that you did with rational functions in pre-calc. Where the function is 0 is where the numerator is equal to 0. Okay, well, that happens when x is equal to 0. And down here, the function is undefined where the denominator is equal to 0. And it doesn't take much effort to come up with x being plus and minus 2 as being the spots where the denominator goes to 0. You take that denominator in the parentheses and solve it out, that's what you're going to get. So our final answer here is our critical values are at x is equal to 0, x is equal to 2, and x is equal to negative 2. Those are the values of x that are going to give us our critical points. Let's take a look at another example here. 4 drops out. All right, now that one's a little bit gross, but at least we're on an interval from 0 to 2 pi because we know that with trig functions there's probably a whole lot of points that are going to give you a value of 0. So let's turn our focus on to finding the derivative of this function. And as I look at this, I'm sort of a little bit, horrified, but at the same time relieved, because it looks like this particular term right here, that's just going to drop out. But for this term, I'm going to need to use, of course, the dear old chain rule in order to pull that off. So as I go to find the derivative dy over dx here, I'm going to wind up getting 6 times the cosine. Well, I better back up here because I'm getting all excited about using the chain rule and forgetting how to do it. So it looks like it's going to be 6 times the cosine of x, because you drop that power by 1. So 3 times 2 for 6, drop the power by 1. And then you have to multiply it by negative sine of x, which is the derivative of our inner function of cosine here. And like we said, okay, so as I go to do that and figure out what values of x are going to make this go to 0, that's the big question. And they have to be starting at 0 and going all the way up to 2 pi, but not inclusive. All right, well, let's start with this part right here. Let's start with the cosine part and figure out where this whole thing will go to 0. Well, that will happen when x is pi over 2 and also 3 pi over 2. Those values are definitely going to give us critical points there, because if you put in pi over 2 or 3 pi over 2, the whole thing multiplies to 0. And you could do something very similar here for the negative sine function, and that, of course, is going to be at 0 and pi, where that goes to 0. So all 4 of these are quadrantal angles. They are going to be our critical values of x. Okay, one more example here. Find the critical values of this function for all x that are less than 5. Domain restriction is kind of nice because that's going to stop us from having values of x that are out of the domain, because we're only interested in things that are in the domain here. So let's go ahead and do this one, and we need to use ye olde product rule on this one, because here's your u and here's your v. So this one's going to be a little bit on the interesting side to do here. Let's see if we can come up with dy over dx for this function. So u prime is 1, so we have our 1, and then our v is going to be the root of 5 minus x, and then we have u, which is x, and then v prime. I'm going to speed that up for everybody's benefit. It's going to be 1/2 times 5 minus x to the negative 1/2. And then I can't forget my chain rule by multiplying by that inner function, so I have to multiply everything by -1. And now I'm going to clean everything up, and I'm going to set this derivative equal to 0 to solve it. And when I clean up this other term, that's not a negative, or not a positive, that's a negative, so let's fix that first. X over 2 times the square root of 5 minus x. So that's what that works out to be when we clean it all up. Okay, now this looks like it's really not all that fun to solve, but trust me, it's not so bad. I'm going to take this entire radical term right here, and I'm going to move it over to the other side, and you're going to see that something rather sneaky happens. And most of my students remember me issuing what I like to call a sneaky trick alert, because this one allows us to multiply both sides by what's in the radical, and when we do that we get x over 2 is equal to 5 minus x. As you multiply radical by itself, poof, the radical goes away if it's just a square root, which is nice. Okay, so now I'm going to multiply everything by 2, and then I'm going to need to move that 2x over to the other side, and then when I divide by 3 I get 10/3, and that is definitely something that is less than 5, so this is a critical value for this particular function. Okay, and that does it for this particular video.